All right, then let's move on, and today we are going to talk about 3 different types of phenomena that light displays. One of them is going to be refraction of light. So what is the meaning of refraction of light? In fact, you have already seen this phenomena. Refraction of light refers to the fact that when light goes from one medium to the other, the light changes its speed, and because of this change in speed, the light might slow down or speed up depending upon what kind of medium it's going, what was the initial medium and what was the final medium. So this phenomena of light slowing down or speeding up when it goes from one kind of medium to the other is called refraction of light. So change in speed of light when light goes from one medium to the other. And what you will see, so for example, light could go from air to water, and what you will see is that the speed of light in water is going to be less than speed of light in air. In fact, speed of light in air or vacuum, remember last time I told you it's 3 times 10 power 8 meters per second, and that is the fastest that anything could go. In fact, matter, anything that has mass, anything in this periodic table can never travel exactly at speed of light in vacuum. The 3 times 10 power 8 meters per second is really the limit. Einstein's theory of relativity is based upon this assumption that no matter can ever travel at speed of light. But light itself travels at speed of light 3 times 10 power 8 meters per second only in vacuum, or we are going to approximate air as roughly vacuum because the air molecules are so far apart that you can almost think of it as very less dense. So it's almost like vacuum. Now what happens when light goes in water, or what happens when light goes in, say, glass? It will slow, or plastic, it will slow down, right? And that's the phenomena that is called refraction of light. And in fact you can see it because when the light will slow down, you will see that it will actually bend. It will go at a different angle, and so you can actually easily see, have you ever put a spoon in water or something? Half of it is in water and half of it is not. You see it kind of looks bent. And it's because of this bending of light that happens because light now is traveling at a different speed. Now before we talk more about refraction of light, let me tell you something about what is called refractive index of a medium. So refractive index of a medium, we can define something called refractive index of a medium. And we are going to give it a name n. This is really defined as the ratio of the speed of light in vacuum to speed of light in that particular medium that you're considering. So symbolically we can say that n is equal to c, speed of light in vacuum, divided by v, where v is the speed of light in that particular medium. So for example, do you know what this ratio, and what will be this ratio? Can this ratio ever be less than 1? Well, we are saying that speed of light in vacuum is the largest thing. So for all things you will see for light in any other medium, so for example if it's in water or if it's in glass or if it's in plastic, this number will always be greater than 1, right? Because v is smaller than c. So for example for glass, n will be roughly 1.33. For sorry, this is for water. For water, n is this. For glass, it's roughly, n is roughly in the ballpark of 1.5, but exactly what it is will depend upon which color of light are you talking about. So for example for glass, for blue light, it might be 1.54. For another color of light it will be 1.56 a little bit different, okay? So it depends upon the color of light. Why is it that it depends upon the color of light? Because it turns, what do you think is changing? When light is going from, say, air to water or air to glass, what do you think is changing? Yeah, actually that's a very good idea, because a point, because it turns out, remember, one thing that we had talked about is this, that C is equal to lambda times F. And this is always, you know, or let's just call it V. V is lambda times F, remember? What remains constant when light goes from, say, air to water, or it goes from air to glass or glass to water? What remains constant is the frequency of light. So frequency of light will not change when it goes from one medium to the other. What will change is its wavelength. So frequency of light remains constant when light goes from one medium to another. But what changes is the wavelength. So for example, in this particular case, if the wavelength changes, we can write it like this. We can say that N, which is equal to C divided by V, C can be written as the frequency times lambda in vacuum, and V can be written as the same frequency, because frequency is not changing, times lambda in that medium. Frequency and frequency get cancelled, and you can see that the refractive index can be defined as lambda in vacuum divided by lambda in the medium. Right? Because frequency does not change. Whether you are in vacuum or whether you are in some medium, frequency is the same. It's lambda that is different. So refractive index can also be defined as the ratio of the wavelength of light in vacuum to the wavelength in that medium. Okay? And for different colors of light, like green light or blue light, violet light, the lambda of the medium is slightly different, right? And lambda is slightly different means that refractive index will be slightly different. You see what I'm saying? So those refractive indices do depend upon the color of light. Now let me tell you something that will tell you exactly how much light should bend, for example, when light refracts from one medium to the other. And we already said that if this is air, let's say this is air, and you are shining some light, when light goes into water, here is the water, light will bend by a certain amount. Why is light bending? It's bending because light is actually flowing down in this case. All right? How do I figure out by how much will light bend due to this bending or due to the change in this wavelength of light? It's given by what's called Snell's law. So let's talk about Snell's law now. Snell's law says that N1 times sine theta 1 should be equal to N2 times sine theta 2. What is N1? N1 and N2 are the refractive indices of medium 1 and medium 2, and theta 1 and theta 2 are the angles at which light is incident or refracted in the two media. So for example, the first medium that we are talking about is air, which is pretty close to vacuum, that has a refractive index N1, and I'm shining this light, and by the way, these angles here are measured with respect to perpendicular or normal. So here, this is the angle theta 1, and then this light at this interface gets refracted by some amount, and the angle becomes theta 2. Right? By the way, do you see that if it was not water, if it was going from air to air, if it's going from air to air, do you see that N1 is the same as N2? In which case theta 1 should be theta 2, so no refraction takes place if the light is going from air to air. It just goes straight. But it's bending because of the fact that the refractive index of the two media is different. So for example, if I told you in this particular case that this is water and it has a larger refractive index, what would you conclude about the angle that this refracted ray makes with the perpendicular or normal? Should it be smaller or larger than this angle that the incident ray makes with the normal? Tell me. Smaller. So for example, let's try to put in some numbers. So here's an example. Suppose N1 is 1 and N2 is 1.33. So that means the second medium is water, let's say. And let's say that the light is incident at some angle theta 1, let's say, which is 30 degrees. The question is, what is theta 2? What is the angle of refraction? This is the angle of refraction. Theta 2, we want to know, and this is the angle of incidence. Using the Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. Do you see that I can write sine theta 2 is equal to n1 sine theta 1 divided by n2? So this will be 1 divided by 1.33 times sine of 30 degrees. By the way, you can already see what should theta 2 be less than theta 1? Yeah, sine of 30 is, by the way, half. So this is, half times 1.33. So you can find theta 2 by saying this is sine inverse of that number, 1 over 2.66. And if you work it out, already you can see theta 2 should be smaller than theta 1, shouldn't it? I mean, do you see that? I mean, like, sine is a sine increases from 0 to 90 degrees as angle increases, right? So sine of 30 is more than 0. Sine of 60 is more than 30. Sine of 90 is more than 60, right? So the thing is, do you see that if n2 is greater than n1, theta 2 should be smaller than theta 1, right? If n2 times sine theta 2 is n1 times sine theta 1, then if n2 is greater than n1, theta 2 should be less than theta 1. So this number, I know, I'm not going to work this out. I don't have a calculator, but whatever it is definitely less than 30 degrees. You can try it at home on your calculator. But does that make sense? So what is the conclusion? The conclusion is that when light goes from a medium that is less dense, such as air, into a medium which is more dense, such as water, the light will actually bend. The refracted light will bend towards the normal, so that theta 2 is smaller than theta 1. Is that making sense? So any time light will go from a medium that is less dense, and by less dense I mean which has a smaller refractive index, to a medium that is more dense, light will bend towards normal. By the way, I could do the opposite. I could shine the light this way at an angle, and then it's going to bend. So basically, if I shine light this way, then we can start calling this angle theta 1, and this angle can be called theta 2. There's nothing in the name. You can always call this angle Harriet and Georgina. It wouldn't matter either. But then you will have to say n1 times sine of Harriet is equal to n2 times sine of Georgina. That might not be such a, convenient way of writing things. But does everybody see that if I actually shine light like this, it will get refracted because of this change in wavelength of light, because of the slowing down of light at an angle theta 2, which is going to be greater than theta 1. Why? Because this time light is going from water, which is a denser medium, which has a higher refractive index, to a rarer medium, which has a lower refractive index. Does that make sense? So light will just trace its path. This way, whatever you see, you can reverse the arrows, you get the same exact thing. So what happens when I shine light, and light goes from, say, for example, water to glass? Tell me which way will it turn? If light is going from water to glass, look at which one is denser. You can see glass is denser, right? It has a higher refractive index. So if I have, say, for example, this is water here, and this is glass here, okay, and light is incident at some angle theta 1, which way will it turn? Will it go this way or will it go this way? Huh? How many people think this one? Yeah, that's the correct one, because since it's going, so basically theta 2 will be smaller than theta 1 because glass is denser than water. Here n1 is 1.33, here n2 is 1.5 something, let's say 5.4 for a particular type of glass. Then you can see for a given color of light, you can see that theta 2 should be smaller than theta 1. Any questions about this? Okay, now here is the thing. We can see already that if suppose light is going from a less dense medium, okay, here is the thing. So let's say that this is air, this is water, and suppose, okay, this is a good picture actually. Suppose I'm shining it like this. Suppose I shine this flashlight like this at some angle theta 1. Do you see it's going away from the normal because this is less dense medium, this is air, right? Now what happens if I increase this angle? If I shine this flashlight at a greater angle of incidence, wouldn't this increase also? It will. All the times n1 times sine theta 1 will be equal to n2 times sine theta 2. Do you see that there will be an angle here at which the angle of refraction will become what? 90 degrees, right? So there will be an angle here. If I'm shining light from a denser medium, let's say this is water which has a refractive index of 1.33, this is air which has, let's call it n1, this is n2, which is, let's say, 1, close to 1, there will be an angle of incidence at which angle of refraction becomes 90 degrees. So this is by theta 2. Does everybody agree that if I keep cranking up this angle, since this is always greater anyway because this is a rarer medium compared to this, there will be a point when this becomes 90 degrees. That angle is called, that angle of incidence is called the critical angle. So this angle theta 1 is equal to theta c, or critical angle, if the refracted light is at 90 degrees. To the normal. So now the question is this: what do you think will happen? What do you think will happen if I make the angle larger than that? Can you tell me what will happen if I make the angle greater than that? Any thoughts on that? If I make this angle of incidence slightly more than this critical angle, this is theta 1 is equal to theta c. Tell me what will happen if I make this angle a little bit more. Go ahead. Yeah, all of the light will actually just reflect here. Nothing will go in that medium at all. All the light will reflect in the same medium. So if I shine like this, all the light will reflect such that the angle of incidence is equal to angle of reflection. And this phenomenon is called total internal reflection. So basically, what is total internal reflection? Let me write it down. When light goes from a dense to a rare medium, to rare medium, and the angle of incidence and theta incidence, which is theta 1, this is theta 1, is greater than theta critical, then light will totally internally reflect. Light will get reflected in the same medium from which it was coming. And this is called total internal reflection. So for example, do you think we can figure out what should be that critical angle for glass? Let's try to see what would be the critical angle for glass. So let's do an example where we'll figure out what is theta c for glass. In order to figure that out for glass which has a refractive index 1.54, let's say, we know that n1 sine theta 1, and this is light going from air to glass. So we know that n1 sine theta 1 is equal to n2 times sine theta 2. So in this case, we have a situation like this. We have light going from glass. This is glass, and refractive index of glass is 1.54, and it's going into air, whose refractive index is 1, and light is going exactly at that angle that we are calling theta critical, such that the angle of refraction, theta 2 is actually 90 degrees, right? So let's plug in the number. N1 here is 1.54 times sine theta 1 is theta critical, and that should be equal to N2, which is N2, which is 1 times sine theta 2, which is sine 90, and sine 90 is what? 1, right? Sine 90 is 1. So from here you can see that sine theta critical is equal to 1 divided by 1.54. In other words, theta critical will be sine inverse of 1 divided by 1.54. Right? This is the critical angle for glass. If the angle of incidence is anything greater than this, the light will totally internally reflect in the same medium. If you choose an angle which is greater than that, light will reflect in the same medium. Let me show you this demonstration over here. I'm going to turn off all the lights here and show you. Here is the demo. Let me turn this off. Okay, so here, watch. I don't know if you can actually see what's happening, but do you see that there is a light that's coming from this source here, and it's going from water. Here is water, and this is on the top is air. The light is going from water to air. Do you still see refracted light into the other medium? Yeah, you still do. Let me make the angle bigger, 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 bigger. Look, do you see now that all the light is going into the same medium? Can you guys see it or not? No? Here is this is the refracted light. I don't know if you are able to see very well, but the point is that now all the light at this point is totally internally reflected. So the light comes in like this and it goes into the same medium. Were you able to see that? So it comes in like this and it gets reflected in the same medium above a critical angle. Any questions like this? Anybody? By the way, do you know that this particular phenomena of total internal reflection is made use of in fiber optics? Like, look at this demonstration here. This is a demo of a fiber optics cable in which, and fiber optics is used all the time. For example, if I were in England and you were trying to call me, the phone message is first going to get converted into electromagnetic waves, and they will travel through this fiber optic cable in the Atlantic Ocean to me. And we don't want to lose that electromagnetic signal, right? We want to retain the signal that originated from me. My sound wave got converted to electromagnetic wave, and that's traveling through this fiber optics cable. You don't want it to be lost to the surrounding. So how do you retain it? You have to make sure that there is a total internal reflection taking place at every point this thing hits the wall. So do you see that this green light actually hits it here, then it gets reflected, then it gets reflected, etc. So that way you retain the signal as opposed to losing it to the surrounding, right? If the light got refracted out, it would be lost. Of course, nothing is without any loss. So there is always some loss even in those fiber optics cables, and that's why they have to once in a while do error correction. They have to keep fixing the thing, but these fiber optics cables are really important in transmitting signals in the electronic industry and also in communication industry. Like, these are real fiber optics cable that are used. You can see what they look like. But the idea is that if total internal reflection is taking place at every point, then the thing won't, the electromagnetic wave or light wave wouldn't go out. This is also a real cable. Is there any question about this? By the way, refraction of light is also used in producing a rainbow kind of a pattern. Why? For example, this is what is called a prism. You know, let me show you a prism over here. Here is this thing called prism. Do you see color of light? White light, when I pass white light through it, you see here a whole spectrum. Why is it that light, when it passes through this thing, it splits into all these different colors? By the way, this phenomena of light splitting into different colors is called dispersion of light. But dispersion of light is because of the fact that different colors of light have different wavelengths for the glass. It just differs a little bit. One of them could be 1.54, one of them could be 1.52, one of them could be 1.53. So then, using this n1 sine theta 1 is equal to n2 sine theta 2, do you see that if the refractive index of glass is a slightly different thing for different colors will bend by different amounts? And then again, here also the same thing happens. Different colors will bend by different amount compared to the normal to that surface. And because of that, light now, white light, which really consists of different colors, has now gotten split, and you can see the different colors. In fact, this is exactly what happens in rainbows also. You know, rainbows are water droplets. So in that case, water droplet will have different wavelength, for slightly different wavelength for different colors of light. And when the water is passing through these droplets, it's getting, you know, separated into different colors that were together in air or vacuum. Because in air or vacuum, all the different colors travel at the same exact speed, right? Is there any question about refraction of light? Anybody? Okay, another thing is, you know, if you wanted to, for example, figure out the height of a of a treasure chest, again, you can make use of refraction of light. For example, if suppose you are here, and people who go fishing, they know about this kind of thing, you know, because if this is your fish, do you know that it always looks elevated when you look from air to the fish? Do you know that? I mean, anybody who goes fishing knows this. Why? Because see, even though the light is really, you are able to see the fish or the chest when light is coming from you to you from this chest. And look, light will go like this, and then it will bend. Now our eyes have this ability to extrapolate the rays of light. And so when we extrapolate this ray of light in our mind, it seems like to us that these light rays are coming from here, and this is where you will see the image of the fish or the image of the chest. Now, if you wanted to know what would be the apparent depth that it will seem like to you is the depth of this thing compared to the actual depth, you can again make use of the refraction of light, and you can say that apparent depth to true depth is equal to the refractive index of in air to refractive index in water. And so in this case you can see n air is obviously 1, so this is roughly 1 divided by n water. So then apparent depth then will be equal to true depth divided by n water. And so let's take an example. Let's say that the true depth, let's say, is 10 meters. You have a treasure chest at 10 meters. What would be the apparent depth? It will be true depth, which is 10 meters, divided by refractive index of water, which is 1.33. So you can see that it will seem like to you that it's actually higher by an amount, true depth divided by 1.33. That's this depth here. Is that making sense? Anybody has any questions? Okay, then we will now move on. And at this point, we are now going to talk about interference of light. You know, when we are explaining reflection of light or refraction of light, you do not necessarily have to think of light as a wave. Even if you think of light as consisting of, you know, moving in these rays in a straight line, that's good enough. for understanding reflection of light and refraction of light. Light doesn't need to be thought of as, a wave. In fact, Newton, long time ago, said, oh, light consists of these particles. He had this corpuscular theory of light. But there's some phenomena that you cannot understand at all if you thought of light, if you didn't think of light as a wave. We have already talked about one of them. What is it? Polarization of light. Polarization is a phenomenon that is only connected with transverse waves. So unless you think of light as a transverse wave, you cannot understand polarization. You have to think of wave nature of light. Okay? Now, today we are going to talk about two more phenomena that can only be understood if you think of light as a wave. One of them is called interference of light. For example, here's the deal. If you think of two narrow slits from which some light is passing, say red light or something, and I'll show you this demonstration. In fact, you have already done it in your PC, I believe. If you think of light passing through two slits, and this is laser light, what do you expect? If you think of light as just something that moves in a straight line, you might say, oh, maybe I'll get two spots in front of those two things, right? Because if there were two slits and I was throwing golf balls across it, those golf balls will just go and hit straight through. That's not what happens for light. What you see instead is that if these slits are narrow enough, what you will find is that on the screen in front of you, instead of seeing just two spots like this, you see bright, dark, bright, dark, bright, dark, bright, dark fringes. And this kind of thing can only be understood if you think of light as a wave. Similarly, we were also going to talk about something called diffraction of light, and that will just be through one slit, and that also cannot be understood if you don't think of light as a wave. What is the phenomenon of diffraction? Basically, the idea is that if light goes through a narrow slit, do you just expect the light to see some light on the wall right in front of it? That's not what you see. What you see is that light spreads out, and you see these, again, very, very wide. In this case, if there's one slit, you see a very broad, bright spot, followed by dark, and then also some bright spots after that. And then again some dark, then again some bright. This kind of a pattern is not expected for a particle. It can only be understood for a wave. Also, the bizarre thing about light going through one slit, or in fact, this is in general true, but when light goes through one slit, as you make the slit narrower and narrower, what will you expect will happen to how wide is the central fringe? How light will flare out? What do you expect? Yeah, it turns out that it's totally contrary to what you would expect. So in other words, the narrower you make the slit, the more light flares out. This cannot be expected of particles, right? You don't expect them to flare out more if you make the slit narrower and not narrower through which particles are going, right? So that means diffraction will definitely also be a phenomenon that can only be explained by wave nature of light. So these are the two things that we are going to talk about today. But before we talk about interference and diffraction one by one, I want to review some of the stuff that you have already done in Physics 1 so that we can understand these things about waves. So do you remember constructive and destructive interference of waves from Physics 1? So basically this is the idea. The idea is that if suppose, let's say that in the interference thing, what we will have is we will have two slits, and we'll pass light through two slits, and this light is a wave, so it will go to different places on the screen. The idea is that if it reaches some point on the screen where both of these light waves are arriving in phase, and by in phase I mean that the crest of one wave is on top of crest, and when the trough of this one arrives, then it's on top of the trough of the other one, and you see what I'm saying? Then those waves are totally in phase, and this kind of an interference at that point on the screen will be called completely constructive interference. You have already learned this in Physics 1 in the context of, for example, sound wave, and you have said, oh, if I have two speakers in my house in two locations, and if I stand at different places in my room, at some place I hear very loud sound because the sound wave from the two speakers are constructively interfering. the crest is on top of crest and the trough is on top of trough. But if I sit in some other place, it doesn't seem as loud at all. In fact, it could almost be zero sound in some locations if it's really a place where waves are destructively interfering. Okay? So this idea applies to light also. So you will see the reason you were seeing bright spots on some places on the screen, very bright spot, is because in those places two light waves from two different slits were going and constructively interfering such that the crest of one was on top of crest of the other one and the trough of one was on top of the trough of the other one. So the net wave that you see, it has twice the amplitude of the individual waves. Is this making sense? On the other hand, you could have a situation in which you could have a completely destructive interference like this, in which case, for example, if light from one source or sound wave from these two speakers, whatever you want to think of it, arrives at some point in the room, what you will see is if every time the trough of this is on top of crest of this and the crest of this is on top of trough of this, etc., at this point, the two light waves or two sound waves are completely destructively interfering. They'll cancel each other out. You will hear no sound, you will see no light. Right? And so basically the idea is that all you have to do is basically look at the two waves that are present at the same location at the same time and add them up. So here trough is on top of crest, 0. Crest is on top of trough, 0. So basically there's no light. There's no wave present there. This is again a wave phenomenon. This kind of an interference will be called completely destructive interference. Of course, in all real situations, what will you get? You will get something that is partially constructive and partially destructive, right? So the amplitude is not twice as much as the individual waves, nor is it completely 0, but something in between. But here we are going to focus today just on the cases where you get completely constructive and completely destructive. We know that things in the middle will be somewhere in between. At least let's just chalk out what should be the condition for seeing very bright spot on the screen and no light at all on the screen if we pass light through two different sources. Okay? This was an experiment that was done by Young, and that's why this experiment is called Young's double slit experiment. Now there's one caveat. What is this? The fact that, do you see that somehow there needs to be some kind of a phase relationship between the light that you're passing through the two sources? Do you see that these two things, for example, have to start at the same phase or start at opposite phase? Because if suppose that there was no relationship between the phase of light that is starting out from here and starting out from here, how could I tell over here whether it's going to be out of phase or in phase? So in other words, you have to tell me, are you sending light through the two sources which are always starting out in phase or always starting out of phase? Because once you tell me, then I can tell you everywhere in this room what should be the pattern due to that particular light. And the sources that have this kind of a relationship with each other that you have to tell me are called coherent sources. Coherent sources means sources for which you have told me that there is a definite phase relation. So when this one sends out a light with crest, this one sends out light with crest also, and now you tell me if this light has traveled a certain distance and this light from this source has traveled a certain distance, are they going to constructively or destructively interfere here, or what? Or will it be some intermediate interference? Do you see what I'm saying? So the idea is this. Let me write it down for you. We need coherent sources for this Young's double slit experiment. By coherent sources, as I said, there should be a definite phase relationship between light from the two slits. Okay, Now, and in fact, laser light is a coherent source of laser is a coherent source of light. So we are going to shine laser light through 2 slits. So let's try to see what we should get if we pass laser light through 2 slits. So here is the situation. We have these 2 slits. There's 1 slit here. There's 1 slit here. Let's say D is the distance between the 2 slits. Here is the screen. And by the way, in our thing, we are going to assume that both of the light here that is starting out in phase. So if this one is crest, this one is crest. If this one's trough, this one's trough. And the question is, if light arrives, say, for example, here in the middle between the 2 slits, right in between. By the way, here, can you tell me, should it arrive in phase or out of phase if the 2 things were in phase? Because we are going to assume that light from the 2 sources are always in phase. What should happen at the center? Should it be in phase? Yeah, it should be in phase. So you should see a bright spot right in between these 2 slits. But the question is, what about maybe someplace over here? You might see that the light that actually takes off from this thing and the light that takes off from here, maybe they have traveled distances in such a way that crest of one light is falling on top of the trough of the other light at this location. And if that's what happens, and these are coherent sources, that means they maintain this phase relationship, you will always see a dark spot there, because that's the place where you will see destructive interference. Do you see what I'm saying? So depending upon what is this length, let's say call this thing length L1, this is called the path length, and this is length L2, path length for the other source, for the other slit. If suppose this path length difference is such that one crest is arriving on top of the trough of the other one, this is going to be a dark spot. Do you know what I'm saying? So you could have a bright and a dark, and a bright and a dark, and a bright and a dark. Similarly here you could have bright and a dark, and a bright and a dark, etc., etc. Now the question is, do you remember? Does anybody remember what should be L2 minus L1 to make sure that we always get bright spot at those locations? Do you remember from again from this course? How can we be sure that if waves are starting in phase, right, that they end up at some spot in phase? What should be L2 minus L1? Yeah, an integer multiple of lambda, of wavelength of light, right? For example, in this particular case, you can see in this case, this light here from here and here, this one is traveling a path length which is 3 times 1/4 of lambda, and this one's traveling 2 times 1/4 of lambda, so they're traveling different distances. L2 and L1 are not the same. But if you look at L2 minus L1, what is it? Lambda. Do you see that? And so waves are always going to be arriving in phase over here. What is the condition for destructive interference? For destructive interference, here are the 2 sources. Do you see that if suppose L2 minus L1 turns out to be a half integer multiple of lambda, right? It's half lambda, 3 halves lambda, or 5 halves lambda. In that case, if they start out in phase, they will end up out of phase. Does that make sense, folks? So basically what we are trying to say then, is this idea something that is familiar to you from physics 1? Because you must have learned this in physics 1 already in the context of other kinds of waves, not light wave, but sound wave, etc. So basically the idea is that for constructive interference, we should have L2 minus L1 absolute value, I don't care which one is bigger, which one is smaller, should be equal to n times lambda, where n can be 0 or 1 or 2, etc. Right? This is completely constructive. Okay, completely destructive interference, where you hear no sound or you see no light, should be where? where L2 minus L1 should be half integer multiple of lambda. So it should be n plus a half times lambda, where n can be, say, 0, 1, 2, etc. Do you see? The two waves are going to be out of phase. So if that's the case, let's try to figure out in our case, suppose we are only given d, and we are given this distance of this thing from the screen, we are given this thing, and in all of the things that we are going to do, this would be a good approximation. D is a lot smaller than capital D. In other words, the distance between the two slits is very, very small compared to the distance of the screen where you're looking at this pattern. This will always be true because this distance is going to be very small. All right, so if this is the case, if D is a lot smaller than capital D, one of the things is we need to know what is L1 minus L2, right? One thing we can do is whatever is the smaller one, we can drop a perpendicular from that one onto the other one. So let's say that we drop a perpendicular from L1 to L2 such that this distance L1 is roughly equal to this. You know, this is a 90-degree angle. Okay, now actually let me just do it with a overhead transparency because I think that my drawing is not going to be as good as the drawing here. So here is the thing. So let me just show you a drawing from your book. So here are the two slits. So source S1, source S2. You are shining light. Now here, it's true, and we are trying to figure out over here, when will this place be constructive, completely constructive interference? When will this place be completely destructive? When will this place be completely constructive? This is what we are trying to figure out. Now, you know, if this screen is very far away, as we said, compared to the distance between the slits, even though two light rays are meeting here, we can roughly assume, it's true that two parallel rays never meet. But you know, if things are really far away and the angle, you know, and they almost, you know, met very, very far away, almost infinitely far away, we can assume that the rays are parallel, at least locally. Do you see what I'm saying? And if we assume that the rays are locally parallel here, because this distance is a lot larger than this, let's say that this angle is theta. And we are trying to figure out at an angle theta, are we going to see constructive interference at this location or destructive? In order to see that, let's go back to this picture here, which is the same. And this time we have dropped a perpendicular from the longer one, from the shorter one onto the longer one. And do you see that this is my path length difference, delta L? Isn't this my delta L? Path length difference, so roughly this is delta L, the path length difference, right? So if that is delta L, the question is, can I figure out what delta L is? Let's look at this geometry here. So in this right angle, and remember this is right angle, right? This thing is right angle, 90-degree angle here because I dropped a perpendicular. So now in this triangle, here is the idea. If this is angle theta, what do you think this is? Is that 90-degree minus theta? Okay, if that is 90-degree minus theta and this angle is theta, in this right angle triangle, what will be this angle? Shouldn't that be theta? Yeah, so this angle should be theta, and that's exactly what you see here. What you see is that if this thing with horizontal is theta, roughly, that means this must be 90 minus theta. This angle, it must be 90 minus theta. And now if I focus on this right angle triangle here, this is 90 degree, this is 90 minus theta, so this angle better be theta, right? Okay, if that angle is theta, from this right angle triangle, can you tell me what should be this path length difference in terms of d and theta? Who wants to tell me? So what is this distance, which is the path length difference delta L in terms of d, the distance between the two slits, and this angle theta? This angle theta tells me in which direction I'm looking. You know, what is this, at what point on the screen I'm looking. Tell me, isn't it d sine theta is equal to delta L from this right angle triangle? So basically what we are finding then from here is that d sine theta is equal to n lambda is for constructive interference, and similarly for destructive interference, what should we have for d sine theta? n plus a half lambda, right? Now in all of the problems, as I said to you, the distance between the slits is going to be very small compared to d, and we are only going to look at those angles theta which are very, very small. So we will only focus here on theta very small, and if that's the case, if theta is very small, then what do we get? If theta is very small, less than say 10 degrees, then it turns out, which is what it's going to be for all of our cases, then it turns out sine theta is roughly equal to tangent of theta, which is roughly equal to theta in radians. You can check this out. You try, for 1 degree, 2 degree, 3 degree angles, and you will see indeed that this is going to be true. If this is true, then what is the condition for constructive interference over there? Do you see we can write d times theta in radians will be roughly equal to n lambda. This is constructive, totally constructive interference. And we will see that d theta, theta in radians should roughly be equal to n plus a half lambda. This is completely destructive. In other words, on the screen at different angles, for example, this is some angle theta here, this is the angle theta. At some angle theta, you are seeing a bright spot here. Bright spot shows the center of the bright spot is completely constructive. That must satisfy the condition d sine theta is equal to n lambda. Here you are seeing a dark spot. That should be some other angle theta for which you have d sine theta is equal to n plus a half lambda. Can you tell me what should be the value of n for the central thing here, central bright spot here? N should be 0, right? What should be n for the first bright spot on the other side? It should be 1. The second bright spot, n equal to 2, n equal to 3. So as you start putting here n equal to 0, 1, 2, 3, you keep seeing these fringes, these things that are called fringes. This is the central bright fringe, the first bright fringe on two sides, the second bright fringe, the third bright fringe, etc. Right? Similarly here, you can put n equal to 0, 1, 2, etc., 3, etc. N equal to 0 will give you the first dark fringe on the two sides of the center. By center, I mean center of between the two slits, right? Do you see that n equal to 2 will be this one on two sides, n equal to 3 will be this, n equal to 4 will be this, n equal to 5 after that, 6 after that. Is that making sense? So let's try to do a problem, okay? So in this problem, let's say that we are given a few things and we have to figure out whether we'll get a bright fringe or a dark fringe. Okay, so let's just do a problem right now. So suppose you're told find the location of the let's say that you're asked find the vertical distance from the center of the second bright fringe. Do you think we could do this? So they're asking you this thing, let's call this y. So the vertical distance from the center, find y3 for the third bright fringe given, this is an example, given that let's say the wavelength of light is, who knows, 500 nanometers, given that the distance of the slit from the screen is, let's say, 1 meter, and let's say that the distance between the two slits is 1 millimeter. So this is 10 power minus 3 meter. Do you think we can figure it out? The fact that it says third bright fringe, that means n must be equal to 3, isn't it? And what it's asking you is this distance. It's asking you what is the distance from the center of this third bright fringe. This is the y. Okay, it shouldn't be that difficult because we can make use of this. So because we are talking about bright fringe, so d sine theta must be n lambda, isn't it? So what we have is d sine theta is equal to n lambda, and n is 3 here. What is the thing? So this is d sine theta 3 is equal to 3 times lambda, right? This is thetas of 3. Now, as we said, can we figure out what is sine theta 3? By the way, sine theta 3 is the same as theta 3, which is the same as tan theta 3 because these angles are very small. So can you tell me from this triangle here, suppose we are looking at this third bright fringe from this triangle, what's the relationship between this y and this distance d? You see what I'm asking? Do you see that tangent of theta will be equal to y3 divided by this d? Is everybody agreeing from that geometry there that tangent of theta 3 will be equal to y3, which is what we have to find, divided by the distance of the screen from the slits? Do you agree with me? But by the way, tan theta 3 is not very different from sine theta 3. And if you don't trust me in the exams, if there are questions like this, please feel free to calculate sine, calculate theta 3, then calculate tan. That's fine with me, but you won't need to because it's not necessary at all. And so what I'm saying is that this is the same as tan. Tan is roughly equal to sine, all right? Theta 3 in radians, this is a good approximation. If that's a good approximation, then we have d times y3 over capital D is equal to 3 times lambda. Do you see that? And what are we looking for? We are solving for y3, aren't we? Aren't we solving for y3, folks? So then, from here you can see y3 turns out to be 3d lambda over d. I'm not going to plug in numbers. This is your answer. All you have to do is plug in the wavelength of light, plug in the distance of the screen from the slit, and plug in little d. Little d is this. It's the distance between the two sources. Capital D is this. It's the distance of the screen from the slits. This is capital D. Anybody has any questions about this? Anybody? All right, then we are going to move on now to the last topic, which is the diffraction of light. And basically, diffraction of light is nothing, as I said, but bending of light when it passes through, say, a narrow slit. And what you will see, which you might find very bizarre, is that the narrower you make the slit, the more light will diffract, or the more light will bend through its aperture. And as I said, this is a general property of any waves. Light, in fact, doesn't diffract as much as sound wave. You know this. Why do you know this? For example, if we open this door and I screamed in this corridor here, do you think people over there in Allen Hall might be able to hear me? Why is that? Because the sound is not traveling in a straight line, it's bending around the aperture, right? It's bending around this opening. And that's why, the sound is diffracting. If suppose everything was dark in Allen Hall and OEH, and if I actually turned, the only place that was lighted was this room, and I opened the door there, do you think that, light will go all the way to Allen Hall? Not necessarily. It will flare a little bit, but not a lot, not as much as sound, right? So light doesn't flare as much, and that is because the wavelength of light is a lot smaller than the wavelength of sound. It turns out that things flare more if the opening of the aperture is comparable to the wavelength of that thing, of that particular wave. So the wavelength of sound is more comparable to the width of the door. So the sound diffracts more. Light has a wavelength, say 500 nanometer or 600 nanometer. That is so small compared to this that it won't diffract very much. Hey, but if we choose a very narrow slit, do you think it'll diffract? Yeah. So if we choose a very narrow slit whose width is comparable to the wavelength of light, then it will show significant diffraction, and we will be able to see it. So let's talk about diffraction of light. And again, what you will see on the screen in this case will be a pattern which is going to be bright dark pattern. So here is the thing, you have some wave that is incident, and the question is what kind of pattern should you see on the screen, and I claim that the pattern that you are going to see will look like this. So here is your opening, and let's say that the opening has a width W. The opening has a width W, here's the screen, and what I'm saying is that when light goes through this, it will flare out, and what you will see on the screen here is a central bright spot that is very wide. Then there will be some dark spots here. Then there will be another bright spot on the two sides which may not be as intense. Then again there will be a dark spot here and the dark spot here. And then again there will be a bright spot. Then again dark spot, this kind of a, but this pattern is not as fine grained as the pattern that you saw with two light sources, the one that we were talking about previously, the interference of light. So this flaring of light, when it passes through any aperture, this flaring is called diffraction, and obviously you can see diffraction is going to be a wave phenomena, right? If you were talking about golf balls going through some slit, it will go just straight through and hit the thing. That's not what we are talking about here. We are talking about light flaring out. And in fact, in a minute, you will see that more is the width, less will be this flaring. You will see that this central bright spot is not going to be as wide if you make the slit wider. On the other hand, if you made the slit narrower, it's going to get wider and wider. So let's focus in this thing, we are going to mostly focus on the width of the central fringe. Now it's very hard for this course for us to actually do the math, all the rigorous math, so it's not given in your book. So the thing is, we are not going to do it either, but I'm going to give you some conceptual argument for figuring out where will be the dark spots. These are the dark spots. You can also call them dark fringes. This is a diffraction pattern. So for example, this is the first dark spot on the two sides, these are the second dark spots on the two sides, third dark spots. Let's try to figure out how to get the first dark spot, for example. What is going on? Why do you get dark spot? So why is it that when light goes from here, from this thing, now we don't have two slits? Why do you think we should get a dark spot at all? Any thoughts, folks? Look, it turns out that you can think that there are lots of point sources even in a given slit itself, right? Can you think of waves going from here, 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 everywhere? And if those waves somehow arrive at this point such that each of them cancel each other out in pairs, so when one of them is crest, the other one is trough, when one of them is crest, the other one is trough, then do you see that the whole thing will cancel each other out? And so in order to understand where should we get the first dark spot, let's actually, and the picture is much better over here in your book. So what we are going to do is we are going to first divide this slit into two parts. So let's divide it into two parts, each of which is going to have a width W over 2, W over 2. So this is first top half and bottom half. Do you see that if light was arriving, if the light was arriving at this point in such a way that, say, the wave from the top of the slit was just out of phase with the wave here in the top of the second half of the slit, suppose this one and this one arrived out of phase. Suppose the one below that, the wave from just below that arrived out of phase with the wave here. Suppose the wave from below this and just below this arrived out of phase here, and the one below this and below this just arrived out of phase there. Do you see that they'll all cancel out? If they were all arriving in pair from the top half and the bottom half, and in pair they were cancelling each other out, so the crest of one was falling on top of the trough of the other one, and that will give us the condition for getting a dark spot. So let's try to find this condition where from the top half and the bottom half of the slit, the wave from here and here are arriving out of phase, from here and here are arriving out of phase, here and here are arriving out of phase. So what would be that condition? Again, well, let's do one thing. We are going to drop up, let's say this is L1, let's say this is L2, and let's say that L2 is longer than L1. Again, we are going to drop a perpendicular from L1 to L2, and so this angle is 90 degree, all right? And actually the picture that is much better is here, so let's just look at this picture here. So here is my whole width, all right? This is my whole width, and we are saying if the wave from the top of this interferes destructively with the wave from here, and the one from here and the one from here destructively interfere, and the one from here and here, and the one from here, then that place on the screen where they're meeting will be a dark spot. So, and by the way, why is it that we are not bothering with the bright spots? Because bright spots are too wide for us to figure out where exactly it is. It's the dark spots that are localized. So then, to find the condition for constructive or destructive interference, do you see that if this is W over 2, again, by the same token that we had talked about last time, shouldn't this angle be theta? It should be, right? So this angle should be theta. And what should be lambda over 2? Which thing here should be lambda over 2 for us to actually get dark spot? Tell me, you know. How much should be lambda over 2? We are saying that the middle of the screen here should be out of phase with the top of the screen here. So do you see that this much here, this distance here, should be lambda over 2 for us to get dark spot? You know, this delta L should be equal to lambda over 2. But this delta L is for this, you know, from here to here, this delta L should be lambda over 2. That means this side is W over 2. Do you understand what I'm saying? So in other words, what would be the condition for getting dark spot? Anybody wants to tell me what should be the condition for getting a dark spot? Huh? Condition for dark spot will be? You know, dark spot will be obviously D, you know, sorry, it'll be the width. What is the width here? W over 2 times sine theta should be equal to, isn't this delta L? That should be equal to what? We are talking about dark spot, right? So this is lambda over 2. We are talking about the first dark spot right now. In other words, what should 2 and 2 get cancelled, and what we have is W sine theta should be equal to lambda. This is the condition for the first dark spot. You know, for the second dark spot, for finding out why should these things be dark here at this point and this point, the second dark spot, how should the waves meet? If we want to know how is it that the wave going from here and here from this screen, all these point sources, how are they interfering out of phase? What we can do, folks, this time, we can divide the screen into 4 equal parts, each with W over 4 width. And then again we can say, hey, if the wave from this 1/4 and this 1/4, you know, interfere destructively over there, and from this 1/4 and this 1/4 interfere destructively, we will get a dark spot. Right? So the second, so this is for the first dark spot. For the second dark spot, we can say we divided the slit into 4 parts, and so W over 4 this time times sine theta should be equal to lambda over 2. And what this says is, you can see, this means W sine theta is equal to 2 times lambda, because one of the 2's get cancelled. Can you see the pattern? This is for the second dark spot. What would be the pattern? Who wants to tell me where should be the third dark spot? Huh? W sine theta should be equal to 3 lambda. The next one will be 4 lambda. So in general, this will be the condition for dark spot, where n is equal to 1, 2, 3, 4, etc. So if you wanted to know, you know, where will be the next dark spot over there and the next one over there, you know, just put n equal to 1. Notice very carefully that in the case of single slit, when we said d sine, in the case of double slit, when we said d sine theta is equal to n lambda, that was for bright spots. Here when we are saying w sine theta is equal to n lambda, this is for dark spots. So for example, let's do a problem. Suppose you had a problem in which you were given again, by the way, suppose we are again, this time we are going to find the width of this. Suppose we are told find the width of this whole thing, y1. So well, the width of this whole thing, if let's call this y1 here, y1 is the half width, then the total width of this will be 2 times y1. Do you think we can find that? The width of the central maximum? We can. Why? Because let's say that we are given something. We are told that who knows, d is equal to 1 meter. We are given w is equal to 10 to the power minus 3 meter. All right, and we are told that the wavelength of light we are using is 450 nanometer, let's say. And we have to find the width of the central fringe. So let's first find y1. We know that the width of the central fringe y is equal to 2 times y1. So we need to find y1. Can we use this thing? If it's the first central fringe, that means what dark spot are we talking about? When we use this thing, w sine theta 1, it should be equal to 1 times lambda. Right? W sine theta 1 is equal to 1 times lambda. So by the way, again, sine theta 1 will be roughly equal to tan theta 1. And can you see from this triangle that tan theta 1, if this is the angle we are talking about, this is theta 1, tan theta 1 will be equal to, this is d times y1 over d is equal to tan theta 1. Does that make sense, folks? So basically what we are saying is y1 divided by d is equal to tan theta 1, which is roughly equal to sine theta 1 if the angle is small. So then here w y1 over d is equal to lambda. From here you can see that y1 turns out to be equal to d lambda over w. And so we have this width of the central bright fringe. It will be just 2 times this, isn't it? I'm not going to plug in the numbers, you do it. Everything is given to you. I already told you capital D is this is the distance between the screen and the slit, W is this, lambda is this, you can find everything. Okay, any questions about this, folks? One last thing that I want to talk about is diffraction through circular aperture. When you are, our eyes have a little hole, or cameras have little holes, and those things are not narrow slits like this. By the way, I had told you that, notice here what happens to the angle. Do you see that sine theta is equal to n lambda over w? So as w increases, theta decreases. Do you see that? So in other words, as w increases, as you make this slit wider and wider, as this thing gets wider and wider, this thing gets narrower and narrower. Do you notice that? So it has this inverse relationship. Now our eyes have some hole which is not a slit like this, but it's actually a circular slit. So the thing is, in a circular case, in the case of a circular slit, what should we see? It turns out the math is very complicated, but the formula turns out to be something very similar, except, so for example, for diffraction through circular aperture, it turns out that w times sine theta is equal to 1.22 times lambda. This is sine theta 1 is equal to 1.22 times lambda. This is where the first dark spot appears. Okay, first dark spot when diffraction happens through circular aperture. And so here you can see theta 1 will roughly be equal to 1.22 lambda over W. This is sine theta 1, which is roughly equal to theta 1. This particular result is a very important result that is called Rayleigh criteria. For resolving two things. Because do you know why is it that, you know, like if right now I'm able to see him and her as two different things, but if I keep moving farther and farther away, there will be a point at which things will start merging into each other. You've seen this in the planes when you start looking at trees and houses, after some time they merge into one thing. And that has to do with this Rayleigh criteria. That has to do with the diffraction effects, because basically what's happening is when I look at you, light is going and forming an image at the retina, but with that image there is also a diffraction pattern associated with you, and similarly with you. And if suppose I'm looking at two things like this, let's say I'm looking at two things, object 1 and object 2, and they are going through this hole of my eye or camera, there is my retina that's forming the pattern. If it turns out that the that the central bright fringe of one person's diffraction pattern or one thing's diffraction pattern is right on top of the first dark spot of the diffraction pattern of the other one, at that point you start losing the distinction between two things. So you will keep, so if I'm close enough right now, the diffraction pattern due to him and her are far apart. So I can see two people apart. As I keep moving away, their diffraction patterns start to overlap. And when the overlap becomes such that the diffraction pattern of one thing's, the central maximum of one person's diffraction pattern starts overlapping with the first minimum of the other person's diffraction pattern right on top of it, that's the point where you are barely able to resolve things. And that is this criteria. This is the point at which you are barely able to resolve it. If suppose you go any farther, if the angle becomes any smaller, you will not be able to resolve things. Does that make sense? So this is basically the Rayleigh criteria. So let's try to do a problem and see if we know how to solve problems using this. So this is about a painting. Have you seen those Seurat's paintings? If anybody who's interested in art, Seurat's painting is a painting in which you use this pointillism, okay, whatever. You use dots to make paintings, and again from very close by you can actually resolve the different dots, but if you go far and far, the whole thing looks like one painting and you don't distinguish between the different dots. So here this problem says that in Seurat's painting you are given that the diameter of the pupil of your eye is 2.5 millimeter, and the diameter, okay, so and some light is coming whose wavelength is given. The question is asking you, when will you not be able to distinguish between things? So do you see that we can make use of this? I'm not going to put in the numbers, let's actually do the quiz quickly, but the point is that if we make use of this, theta is equal to 1.22 lambda over W, and if you are given what is the width, the diameter of your pupil of the eye, if you are given the wavelength of light, you ought to be able to figure out theta, right? But now how is theta related to his two dots here? Here is the thing, suppose you are standing here, this is important folks, because this kind of thing could be there on your test. The thing is, if suppose this is theta 1, right? And suppose this is the distance where I'm standing, this is my eye, this is where I'm standing, this is some distance L. First of all, this distance is so large, let's say that the distance between two spots is S. Do you know this, that if L is very large compared to S is equal to L times theta? You have learned this in circles and those kinds of cases, right? So S is equal to L times theta. And so in other words, from here you can see that theta is equal to S over L. So here, for example, I can put, instead of theta, S over L is equal to 1.22 lambda over W. And you might have at least one question that actually relates to this kind of thing. So basically, if you know the width of the diameter of your eye, if you know the wavelength of light, if you know, what is this L? how far away you are from Seurat's painting, for example, and S is the distance between two dots. You know, the question is, can you resolve these two dots if they are that close, or can you resolve these two people? It doesn't have to be Seurat's painting. It could be, I could ask you, you know, can you resolve these two people if the distance S between them is this, and you are standing that far away from them? And again, you will be able to, you know, figure out. So you could be asked, what is the distance S at which you are barely able to resolve them? And this will be the distance S where you are barely able to resolve them. Does that make sense? So, sorry, this will be the distance L at which they are barely resolved. Any larger distance than this, you will not be able to resolve them. They'll kind of start overlapping. Does that make sense? If L is any larger than this, given by this equation, you will not be able to resolve two things that are S apart. Is that making sense? The top pattern here is the pattern from the double slit, and you can see that there are bright and dark fringes here. The bottom pattern is actually for a single slit, which is exactly identical to the two slits that we have for the double slit, and you can see that in the bottom one we are only seeing the broad pattern. So we are seeing the central fringe here, and then we are seeing these side bands that are very difficult to see. So basically what's happening in the double slit is that within the central bright fringe you are getting some interference from the two slits, because of which the central bright fringe is getting divided into bright, dark, bright, dark, bright, dark fringes. And so basically a single slit pattern gets an additional pattern because of the fact that there are two slits. Okay.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.